In this kinetics video, we are going to discuss a couple of items. Firstly, we're going to look at the Arrhenius equation to calculate activation energy. And then we're going to look at the Eyring equation and see the similarities and the benefits to the latter Eyring equation. Okay, so let's start by looking at this profile of reaction energy profile. If we look, we can see it's a plot of energy on the y-axis against progression of reaction on the x-axis. We've got reactants going to get products. In this specific example, we have an exothermic reaction. We know that because the products are lower in energy than the reactants. And we have an activation energy hump that would impede a spontaneous change. We can annotate the species here in the middle. We can say the activated complex. And the activated complex, we can annotate. In fact, let's get rid of the black ink. Let's see. There we go. Let's go for okay, there we go. So the activated complex, we can label with a double dagger like this. So we can say that this is the activated complex. It's not stable. Which means it's not isolatable, not able. Uh-oh. I might regret putting this out there. Isolate. I'm just going to say, I'm going to chicken out and say not able to isolate. Not able to isolate. That I know I've spelled correctly. Okay, and we know that we have an equation that represents the rate constant, K, that we saw previously, to the activation energy, EA. And this is known as the Arrhenius equation. Arrhenius equation. Okay. So that's that for now. Let me clear my annotations so that we can scroll. Okay, so we've got the Arrhenius equation, which we'll talk about. We'll go into a bit more detail about what the Arrhenius equation does and doesn't say in a few minutes. But let's look at the effective temperature on the Arrhenius equation. So if you look at this plot here, we've got a different plot now. It's fraction of molecules on the y-axis, kinetic energy on the x. And we can see that as you increase the temperature of a reaction from a temperature T1 to a temperature T2, the area under this curve must be constant. So you can see if the curve gets shorter, it has to get wider. So notice that in doing so, in getting wider, we've actually increased the number of molecules, the fraction of molecules that have have at least got enough energy to surpass the activation energy threshold. So we've effectively increased the reaction rate because now we've got more molecules with sufficient energy to react. And we can rationalize that. This is our first experimental insight into the Arrhenius equation. So we know that rate, we've seen previously with rate laws that rate is K, let's say it's bimolecular, let's say it's second order. So rate is rate constant A to the second order. So we know that rate is proportional to rate constant, which is this thing here. And we know that the rate constant is proportional to whatever A is. Now, A must be proportional to temperature. If we understand this exponential decay, and K is proportional to A, which is proportional to temperature, which is proportional to e to the minus 1 over temperature. So this is the important relationship here. Temperature as a coefficient, and then 1 over temperature as an exponential decay. So e to the minus, this is an exponential decay. Which essentially means that this thing decays. Now, if this is an exponential decay that's proportional to temperature, then we would expect the decay to happen quicker with temperature. And as temperature gets larger down here, the decay is going to be less. So if we look at this part of the equation here, so as temperature increases, the decay decreases. And that's why essentially it rises up. It doesn't decay as quick, so the slope is less than it was here. Its ability to go to 0 is lower. Okay, so we have a greater fraction that's above the activation energy. Okay. We'll say more about what that constant A was in a second when we look in a bit more detail at the Arrhenius equation. Okay, so we've got temperature. We're talking about the effect of temperature on rate, or the consequences of change in temperature on reaction rate. So we can see from the Arrhenius equation that it's a straight line equation. So for example, we know that you've got the rate constant is A e to the minus activation energy over RT. Well, if I want to make this exponent a coefficient, I could just take logs. So take natural log of both sides. So log A, then this exponent becomes a coefficient. So we've got EA over R 1 over T, and we can see that that's a Y is mx plus b equation. Okay, so if we plot on the y-axis log the rate constant, on the x-axis we can plot 1 over temperature, and then we have the negative slope, which is our activation energy over R. Then we can see it's easily plotted on a spreadsheet, etc. My students don't have to worry too much about this expression for now. It might become relevant a bit later when we look at the Eyring equation, but I just link it to, it looks similar in form to the Gibbs free energy equation that we'll see in due time. Okay. So we've got our straight line form of the Arrhenius equation. Now let's take a second to look more at this constant A. We said previously in this video that the A is proportional to temperature. We knew that because just of dimensional analysis, if we have an exponential decay that's proportional to temperature, the coefficient preceding it must be proportional to temperature also. A is known as a frequency factor, and this is going to become important later on when we really look in detail at the frequency factor. The hint moving forward is that frequency is proportional to energy, so we're going to link this back to energy again. If you think of your quantum mechanical concept of energy, energy being Planck's constant times by frequency, then that will be a link back to something hopefully you've seen before. So A is the frequency factor. It's specific for certain chemical, and it basically tells us the number of times the reactant approaches the activation barrier per unit time. So this is a concrete way to think of, frequency of watt, energy of watt. So you can think of it in terms of this if you like. Okay, let's see if there's anything here. So again, we've got either the regular form of the Arrhenius equation or the log form that we could do as a y is mx plus b style equation on a spreadsheet. So we've said that the A is this frequency factor. Now let's look at the other part of the Arrhenius equation, which is this exponential decay. So this exponential decay essentially is a number between 0 and 1, at least that's how you can think of it, that represents the fraction of molecules that have enough energy to make it over the activation energy barrier on a given approach. Or you could think of it, it's the fraction of approaches that are actually successful and result in product. So these are concrete ways to think of a more abstract equation. I would say that none of these ways of thinking of it are perfect, but it's a way to contextualize what the equation is trying to tell you. It's an interpretation. Okay, we're going to go into a bit more detail now, looking at this frequency factor A. A can be thought of as a product of two items, an orientation factor P, which we won't spend too much time mentioning because it's not that interesting. And something that's much more interesting is the collision frequency. So we're going to spend a little bit of time looking at the collision frequency now. And we've called that Z here. Actually, we're going to look at the collision frequency in a second. It's coming up. If we take the log form of the Arrhenius equation, let's say we didn't know the frequency factor A, there's a way to get rid of it because it's constant for a given chemical process. If we take the same chemical process at two different temperatures, so we've essentially rewritten the Arrhenius equation twice here, but we've labeled temperature T2 versus T1. So you could think that a temperature T2 will have its own rate constant because rate constant is temperature dependent. And also we've labeled, because of T1 here, we've labeled K1 here. But notice the frequency factor A doesn't change because it's a constant. Okay, it's got a complicated temperature dependency, but overall it's a constant. So then if we take the difference between these two expressions, so log K2 minus log K1, we just take the difference between the Arrhenius expressions, So the frequency factor log A just cancels because we have a log A at temperature T2, and then we subtract the same constant from a temperature T1. So these log A terms cancel. And then we're left with another form, another way of thinking about the Arrhenius equation, which is if you have two temperatures and two rate constants. And this is a nice way to get rid of that rate frequency factor if you don't know it. In looking at the Arrhenius equation, you can probably notice one of the problems, one of the limitations with the Arrhenius equation. You can just about notice it. The R gives it away. R is the ideal gas constant, so there's a link here with use only with gases. We'll make that link a bit more concrete, and the limit of the Arrhenius equation more concretely limited to gases in the following discussion. Okay, so here we have an energy profile. We have reactants on the left. We have an activation energy barrier, a small one. It's only 10.5 kilojoules per mole. We have the activation complex, the activated complex here, which we can annotate. Remember, we use that double dagger. So it's not stable, it's not isolatable. And then if we surmount this energy hump, we can decay to products. Now, if we have an energy profile like this, with its low activation energy, we'd expect a large rate constant and a fast forward reaction, okay? Read backwards, this means that the reverse reaction would be much slower. So let's have a look at why that makes sense, if it doesn't already make sense. We essentially just read it in reverse, and obviously the hump to go backwards is obviously much higher. So we've got all this energy to overcome here, which is the same reaction as above, but in reverse. We now have a high activation energy, therefore a small rate constant and a slow reverse reaction. So that's straightforward. So something that's kinetically favored in one direction will be kinetically disfavored in the opposite direction. Okay, here's where we're going to look at the frequency factor in a bit more detail. So imagine, I might have to draw over this a little bit. Okay, because it didn't come out incredibly well. So imagine this is a cylinder. And you've got a molecule A, gas molecule, and it's on a trajectory scooping out a volume. So it's on this trajectory here, and as it moves, it's going to scoop out a volume. So we can see that as this molecule A scoops out a volume, it's going to be in the presence of other molecules, right? It's in the gas phase. So if it's on a collision course this way, it could hit this molecule. It might hit this one, but it might miss this molecule, okay, if it's not in its direct line of path. We know from our discussion, or hopefully from your background in Brownian motion, and mean free path. So I'll have other videos on Brownian motion and mean free path. But you'll recognize these equations hopefully from that discussion. That as this molecule moves, it will scoop out a volume V, which essentially is the area of this disk, which is pi r squared, where here I've written r, the radius, as d. So pi d squared here just means pi r squared. And then, so that's the area. Then basically the length is proportional to the average velocity, u line. So this is the average velocity. Okay. And the average velocity is the square root of 8 RT over pi m. M is the molar mass of whatever this molecule A is. So whatever this molecule A is over here. And R is the ideal gas constant, T is temperature in kelvins. Okay. And we're keeping in mind now our Arrhenius equation. So this is our Arrhenius equation. Where the frequency factor A is Pz, where P is the orientation factor, which is a constant that we're not really going to pay. It's going to correct our Z value later. And Z is the, I think previously I called it the, what did I call it? I've called it the collision frequency or the rate frequency. So recall that Z there. So now we're going to spend a bit more time looking at what that Z is. So let's say Z, the collision frequency or the collision rate. So I've called it collision rate here. You can call it collision frequency if you like. Because rate is proportional to frequency. Okay, so anyway, whatever you call it, let's say it's Z. Now Z here is the number of molecules you have, the number of A's that you have per unit volume times by the volume of this cylinder here. So we can call this the volume of this cylinder, which is supposed to be the void etched out by molecule A that's moving. Okay, well, we know that the volume of this cylinder is pi d squared average velocity. So we can replace V cylinder with pi d squared average velocity. We know from our prior discussions of mean free path that we have a root 2 in here to correct our value. So we get this approximately equal to value, and we make it exactly equal to for reasons that are kind of important, trivial but important, and you can look at some notes on mean free path if you really want to know where that factor of root 2 comes from. Okay. So I'm going to have to get rid of my annotations so I can scroll effectively. Okay. So we've got, let me get this here. So, okay, so far so good. So we're just having some labels in here. So if we take our equation, which was that this collision rate or collision frequency, which is root 2 n over v times by pi d squared average velocity. And we already said that average velocity was 8 RT over pi molar mass. Then we can effectively take the root 8 out, and we're left with just RT. We can, so this root 2, we know where that came from. This root 8 here, we just take this root 8 out. So to get rid of it, what else do we have? We have, we've got a pi squared here. Where did this pi squared come from? Well, we effectively want to move this pi into the root. So this pi here, we actually want to merge into that square root. So we want to take the 8 out, and we want to put the pi in. Well, if we put a pi in, or rather, if we wanted to take that pi squared out again, it would return pi because we'd cancel the square here with the square root and it would just be pi again. So this appearance of pi squared is just because we've moved this pi into the square root. And now we can see that this denominator pi is going to cancel one of those, and that's why we've lost the pi in the denominator. That's why we only have one pi left in the numerator. And root 2 multiplied by root 8 gives us this 4. So we can see that this 4 is just root 2 multiplied by root 8. Okay, and everything else is everything else. Okay, so now we've got a new expression for our collision rate. Okay, so far so good. So let me get rid of those annotations so I can scroll down. Okay. Okay, so we've got that new collision rate, which is 4n over vd squared, and then the radical of pi RT over molar mass. However, that's for one object A moving through that volume. However, since collisions, and we're looking at collision theory now, since collisions involve two molecules at least, you can't collide with yourself. You need to collide with another version of you, potentially. But since collisions involve two molecules, total collisions per unit time, we have this factor of 2 here. Oh, we've got to introduce a half because if collisions involve 2 and you're looking at one object, then you've got to multiply by a half to get 1. Okay, so we have this factor of a half here. So we've introduced this factor of a half, acknowledging that collisions must involve 2 molecules, but we've only been looking at 1 really. So we have this factor of a half. Okay. So here, AA, we've labeled the collision rate Z with the AA, where here we just acknowledge that we need the collision of A with A to give products. Okay. So if we add that factor of a half back in, then we can see that we've got some canceling out to do. 2 goes into the self once, goes into this twice. And then we've got n multiplied by n, which is n squared, v multiplied by v, which is v squared. So we have this overall expression here. Okay, so again, this is just to remind each other what this is. This is the collision, the frequency factor or the collision rate, the collision frequency or the collision rate, no matter, depending on what you want to call it, that's embedded within A within the Arrhenius equation. Okay, so I'm going to clear my annotation so I can scroll. Okay, so just to give you a feel for plugging some numbers in, And I try not to do this too much in these videos because that's what homework's for, right? But just to give you a feel of how to plug some numbers in. And this calculation is actually important because it will give you an understanding for what it's like to be a molecule. So the question reads, calculate the collision frequency for a molecule in a sample of oxygen at 1 atmospheric pressure and 25 degrees Celsius. Let the molecular oxygen diameter be 2.92 by 10 to the negative 10 meter or 2.92 angstrom. So we've got our equation. The collision rate or the collision frequency Z1 is 4 multiplied by the number of objects per unit volume, the radius squared or d squared, where here d is the radius of our fictitious volume that we're carving out while we move, multiplied by root pi RT over radical m. So just to remind you, this equation is this first equation that we looked at here, Z1. We'll come back to this second one in a second. And once we look at the answer, I'll comment on why we're looking at the initial equation and not the latter one. Okay, so we've got this equation. Let's plug some numbers in. So let n be, let n over v equal Avogadro's number Na, P over RT. So we know this from the ideal gas law. So recall we've got PV is nRT. So if we do, so you can see that's where this comes from here. So the ideal gas law. You can just manipulate that a little bit and you'll see that's where it comes from. Okay, so that means we've got Avogadro's number, which is 6.022 by 10 to the 23 reciprocal moles. We were told the pressure was 1 atmospheric pressure. We've got the ideal gas constant, 0.08206 liter atmosphere per mole Kelvin. And we remember to convert 25 Celsius to Kelvin. We add 273.15 and we get a Kelvin temperature of 298.15 Kelvin. We crunch that all together and we get an N over V value of 2.46 by 10 to the 25th power in units of reciprocal meter cubed. And once we have that, we can, so that's N over V, we can multiply by 4. We multiply by the diameter squared, the radius of our tube, our cylinder, fictitious cylinder that we're traveling through. And then we have the radical component at the end. I'll scroll down to see. We've got the pi. Now we have to be kind of careful here, because we were using the ideal gas equation here based on the units. We used one numerical value of the ideal gas constant. Now we're talking about energy. We need to use another, not the other, because there are several, but another numerical answer to the ideal gas constant in units of energy. So we've got 8.314 joule per mole per Kelvin. Temperature and then molar mass, we have to convert to kilogram. So we've got 32 grams even for a molecule of oxygen. We convert that to kilogram. And then we remember to take the radical, etc., plug and chug. And then if we've calculated it correctly, we get a collision rate of 4.1388 by 10 to the 9 reciprocal seconds. So this is a frequency order of magnitude 1 billion per second. So this represents the average number of collisions experienced by each molecule of oxygen in 1 second. So I felt that calculation was important because not only does it plug and chug some numbers into the equation we've been looking at, but it also gives you a feel, order of magnitude for how busy you would be if you were an oxygen molecule, even at room temperature in a gas. So order of magnitude, billion collisions per second. So you would be advised to keep that in mind. Okay. So scrolling down, oh, I think I said I'd comment on why we use that equation. We were interested here, if you were one oxygen molecule, just moving through your day inside this fictitious volume. So that's what we were interested in looking at, rather than looking at the collision of an oxygen with another oxygen. So it made sense to use the initial formulation of Z. Okay, reaction dynamics. Okay, now we're going to look at the latter formulation of Z, where we have a collision between 2A molecules. So it's reiterated here for convenience. So the rate of collision per unit volume between 2A molecules, ZAA I've called it here, is twice the radius of A over multiplied by the radical of pi RT over the molar mass, multiplied by N over V squared. Okay. Now, we're considering a chemical reaction where we have A and another copy of itself to give a product. Now, the activation energy, we know the fraction of molecules with sufficient energy to overcome the barrier from our previous discussion of the Arrhenius equation, or our earlier discussion of, we're still looking at the Arrhenius equation, for our earlier discussion of it, the fraction was this exponential decay, e to the minus EA over RT. Now, effective collisions are going to decrease the effective collisions involve 2A molecules. So an effective collision lowers the pool by 2A molecules. Okay, that makes sense. So the rate of change of A molecules per unit volume is going to be this factor here, a loss of 2. So let me annotate this a little bit. So this factor here is a decrease of 2A molecules. That's why we have this loss of 2. And then everything else here is going to be the Arrhenius equation. So just to try and frame this to make it look a bit more like the Arrhenius equation. So I think it was on the previous page. I'm just trying to skim back to the previous page to see where I wrote it initially. Let's see. Okay, yeah. So if you look here, let's take this one. This is the Arrhenius equation, right? So this is K, our rate constant, which we know is PZ. Again, we're going to ignore P a little bit here, but we're looking at Z, e to the minus EA over RT. So that's our Arrhenius equation. Okay. So just to keep that in mind, and we know what that 2 is. Okay, so now we take our Z value, which was up top. So now we're just going to plug our values in. So this and this was our Z value from up top. So you can just about see it in this box here. If you scroll back to that box, or if you can see it, I've got my my screen in the way, so I can't really see it. But you can, if you refer back to that, let me see if I can do it actually. It's hard to annotate and scroll on these things. Yeah, so you can see here the ZAA. So if I get it back there, okay. Okay, so we know where the -2 comes from, we know where everything else comes from, and then we've got this exponential decay from the Arrhenius equation. Okay, so hopefully we can appreciate where all that stuff comes from. Okay, so I'm really gonna have to scroll now, so I'll have to get rid of these annotations, and then I will scroll and give more annotations. Let's try and get a chunk. Okay. Yes. Okay, if I can keep it there, that'll probably be good. All right. Okay, so so we understood everything up to here, I believe. So everything up to here, I think we've just annotated. Okay, since A and A go to give products, we know from our rate expression that the rate is negative, because if we look at a reactant A, the concentration of A is going to decrease, so we need to multiply it by a negative to make it a positive rate. The coefficient 1/2 is because there's 2 of them here. So the molar coefficient is 2. So this molar coefficient here is because there's 2 lots of A. So it's that molar coefficient 2 here. Okay, and we've got the change in A per unit time. Okay, so we've seen that before. That's the rate expression. Okay, so this thing here is the rate expression. From a previous video. And we're going to let NAA, so this thing here, we're going to let that equal N over V. Okay, so if you let NAA, Avogadro's number multiplied by concentration, we're going to let that equal N over V. And if you look at the units, you'll, oh, I've written it here. If you look at the units, you can satiate your need to know why that's the case. So if we look at units, we've got Avogadro's number, which is 1 over mole. And then molarity is mole per liter. So we've got 1 over liter, or 1 over volume, I guess, which if you look in our earlier calculation, we calculated it, I think, in reciprocal meter cubed. So we know it's a volume. Okay. Okay, so that hopefully makes sense. So let's scroll a little bit and manipulate this equation a little bit more. Okay, so I don't know if you can see where this came from, so I'll try and annotate maybe this a little bit more so I can fill in some of the gaps. So starting from here, if we know that this is the rate here, then we know that the change per unit time of A is minus twice the rate. Okay. Or if I put my brackets in a better place, I'll put the brackets around the 2, right? I'll make a bit more sense. Okay, so from this rate expression, we can say that this change here, and we know by, well, actually we can leave that there. Okay, so, oh, that's what I wanted to write. So we know also that this is going to be minus 2 times by the rate. The rate is going to be rate constant a squared. A squared because it's second order in A here, because I've got, I'm looking at a bimolecular reaction, I guess. Okay, so I know what K is. I know that, let's see. I know. Well, I've scrolled away from it now, so that's a bother. Okay, let me, without erasing it, I'll need to scroll back up. Okay, so remember this equation here, our -2 and everything else, the Z equation here, it had this N over V squared. All right, we're going to come back to that in a second. All right, maybe I can come back to it right now. Okay, so that N over V squared is something I'm going to have to come back to. Okay, so to understand what this, let's see. Okay, so to understand where this A squared has come from and etc. So we know that, let's see if I can make this as clear as possible. So we know that rate is K A squared. Okay, if it's order, let's say it's order 1 in A, and order 1 in that A, and there's 2 A's, it's order 2. So let's assume that this bimolecular process is second order. So here we can just read into the fact that the number 2 here, the second order, is just the number of A's needed to successfully be present at a reactive site. Okay. And we know that, what did we say? Yes. We know that N over V is NAA, which is from here. Okay. Then this implies that rate is K, and then A squared is our N over V squared, which is just our NA squared, A squared, right? Okay. So we've got K NA squared, A squared. So then if we write this down as our overall rate expression, so we've got essentially rate is K A squared Let me get this arrow out the way. Then we've got this. We've got a -2. So I'm writing the z value again now. 2d squared pi RT over molar mass radical. Then we had e to the minus EA over RT. Then we had n over v squared, but n over v is just NA A, so n over v squared is NA squared A squared. Okay. And we know that that's equal to minus a half dA by dt, which is written up there somewhere. I think it's written up here. Okay. Then if I want to look at the rate of change of A, then I would have to basically combine this minus a half with this one. So I could say see, I'm not making a very clear job of this, am I? I might have to insert, I think what I'll do, I think I'll insert a slide because the problem is I don't have a lot of space and I can't see what I've written, and then I keep on having to erase it because of the technology. So I'll come back to that in a second because it's not as clear. Well, it's not clear, period. I'll come back to that in a second. But until I do, trust for now that the rate constant K is going to be given by this expression here. (2d squared Avogadro's number pi RT over the molar mass m, exponential decay e to the minus EA over RT. So this essentially is, if you recall, we've got the Arrhenius equation, which was our PZ e to the minus EA over RT. Then all of this stuff is the new way to think of Z in our Arrhenius equation, so this rate frequency. In reality, measured K values are always fractions of the calculated K value because of other factors such as orientation. So this orientation is P. So orientation factor, or the steric factor, which is just a fraction, but we can have a look at that in a second. So let's see if I have space to look at that. In fact, why don't I, before I move on with this, why don't I quickly go to a blank document so I can do a better job at trying to make clear the connection that I don't think I made clear just now. Okay, so let's have a look. So this is to try and justify where that final value of Z was coming from. So we initially had ZAA is 2D squared pi RT over the molar mass. This was a radical. and then we had n over v squared. Okay, so that's what we had. Then we had, since A plus A to give products, I think we said reduces to A, so takes away 2 molecules of A, then we had this -2 in front here. So we said the rate of change in n over v is -2, and then we had ZAA e to the minus EA over RT. Okay. And if we plug in for ZAA, then we've just got -2 to d squared pi RT over the molar mass square root n over v squared, which will keep as n over v squared for now. Okay, so that's just to try and recap on what was on that previous slide. So we also know that rate for A is -1/2 dA by dt. So we know that dA by dt, actually, no, we don't need to do that. We don't need to do that. So we know that rate is that, okay? And we know that the rate is also equal to K A2. Okay, so this is just like we've done in the previous video, setting the rate expression equal to the rate law. And we now have a bit more information about how complicated the rate constant K can be. Okay, so the goal now is to try and see how we can formulate a real understanding of what this rate constant is in the or what the Z factor is in the Arrhenius rate constant expression. Okay. So so let's see. So what do I want to show you now? I want to show you yes, okay. So the rate expression is the rate constant. It's also equal to 1/2 d by dt and a since n over v is equal to NAA. Okay, so we've got these equivalents here. Okay, which will help us, hopefully. Okay, so so let's see. So we've got so we've got rate is -1/2. Let's see. Yeah. d by dt NAA, right? So I'm just rewriting this bit here. And that's equal to let's see. Actually, I don't even need to. I'm sorry, I don't need to do that. This is all about manipulating it. It's easy to do, but it's hard to explain how to do it. So if I look at this top thing here, let me box this. I should be able to get away with it by just looking at this, right? Okay. I think that's how I can just do it quickly. Okay. So I've got d by dt. Now n over v is NAA. All right. And that's equal to let's see. So I've got to make this -2. Let's see, this -2 cancel with this thing here, which essentially is the rate constant, right? So I've then got -1/2 and then I've got -1/2, and then I have (2d² pi RT over that, and then I've got n over v squared, which is NAA squared. Okay. So it's basically set in different forms of a rate equal to itself in a way that you can cancel things. So now I've got an NA here. I can cancel one of these guys. And then I've got, so then if I rewrite, I've got my 2. So the -2 and the half here cancel each other out. So then if I rewrite that, I should have the rate of change of A is 2 d² pi. Oh, and I forgot my exponent, which is always amazing. So I forgot to write my exponent here. Okay. It should be, I'll just tack it on here. EA over RT. All right. So then I've got what's left is 2d² pi RT over the molar mass of the compound. I've got one factor of Avogadro's number. I've got A squared, and then I've got my exponent e to the A over RT. Okay. So if you interpret this, this says essentially the rate. And then if I rewrite it the way it looks originally, I'll just swap some of these around a bit. We've got 2d squared. Bring the Na next for no good reason. And then pi RT over the molar mass. E to the minus EA over RT A squared. Well, this just becomes K, right? This whole thing is just K, the rate constant. So we've got rate is K A squared. Okay, so hopefully that's a little bit clearer. It takes a little bit of playing around, but it's just a little bit of basic algebra. You just play around with it till it looks like that. Okay, so let's go back to our initial offering. Okay, so we have K, it looks like that. And then we can just mention briefly the steric factor. So here, okay, the steric factor here is 0.16. So let's say we have two lots of NaCl, which decays to give two lots of NO plus Cl2. Then you can appreciate why the K alone wouldn't be the full story. You'd have a fraction of K because of orientation, and you can think about your notes on quantum mechanics about how the orbitals have to have a certain orientation. So if you had two molecules of ONCl approaching like this, you might not have any reaction NR. But if you have them approaching like this, then it's much easier to see how you could form a Cl bond and then have two lots of NO left over. Okay, I have some notes here on the Eyring equation. Rather than have you read through it on the video, I was just gonna basically just write something on an extra document. So let's go back to these. This page I used to try and make a bit clearer something else. Okay, so let's say a few words about the Eyring equation. Okay. So essentially, let's look at it and then we can see how it compares and contrasts with the Arrhenius equation. So the Eyring equation, the rate constant is Boltzmann's constant, Kb, it's a lowercase k, Kelvin temperature over Planck's constant, and then e to the minus Gibbs free energy of the activation state over RT. So we can compare this with the Arrhenius equation. That we've just spent a long time looking at. Rate constant is A e to the minus activation energy over RT. And the Arrhenius equation is limited because it's only for gases. And this is for gases and other states. So the Eyring equation is more versatile. If you think back to the previous part of the video, go back and have a look. You can see why when we went in and looked at Z, the Z part that had this pi RT over M. So this is one of the big things that makes it gas central. Gas is relevant. Okay, the Eyring equation is a bit more robust. It's got other thermodynamic properties in it that make it a bit more versatile. Okay, and the ones I wanted to point out to you are as follows. Okay. I'll try. So we'll be looking at this video before thermodynamics. So the notes I've originally given will have a couple of thermodynamic features in it that will make a bit more sense after you've looked at thermodynamics. So to try and keep this a bit more kinetics oriented for now, let's say consider consider A plus B to give C. All right, so we can say that the rate is a rate constant A, B. So this is a bit more focused on kinetics only. And well, actually, I won't even say that. Without going into too much thermodynamics, okay, I would say, I'll just rewrite. I'll just make it even simpler. Let's look at what we have. So Boltzmann's constant temperature over Planck's constant, e to the minus. Okay. Compare it back with the Arrhenius equation. Okay, so Gibbs free energy is a type of energy. So this is Gibbs free energy of the transition state. We can see the double dagger here. We'll worry a bit more about Gibbs free energy when we look at thermodynamics. But for now, let's just say it's a type of energy. So that's what they both have in common, an energy, an exponential decay. So let's look here at this. We said previously that this was a frequency factor. That's what we called it, frequency factor. So by analogy, we know that this must be a frequency factor also. And we know from quantum mechanics, let's get in black again. We know from quantum mechanics that frequency, let's call it nu, is proportional to energy. And we know that energy essentially, a way to look at energy is the product of Boltzmann's constant and temperature. So if you think of a wave like in quantum mechanics, you could have Boltzmann's constant T over 2 here, Boltzmann's constant T over 2 here. So overall, you have Boltzmann's constant T. Okay, so we have an energy here. So this is proportional to an energy term. So we have an energy term and an energy term, or another way to think of it, you have a temperature and a temperature. So this formulation this formulation of what this means, this frequency factor here in the Eyring equation, even without going into the thermodynamics and the notes, it starts to make sense that that would be what it is. Okay. So if I can scroll down a little bit. Okay. So again, if I write K is Boltzmann's constant T over Planck's constant, e to the minus Gibbs free energy over RT. Just like the Arrhenius equation, if I log it, I could have log K is log KBT over H minus Gibbs free energy over R 1 over T. And there you would have a Y is B plus MX. So you'd have a negative slope, which would be minus Gibbs free energy over R. You'd plot this 1 over temperature. You could have log K if you like. And obviously the intercept would be the intercept here. This would be log Boltzmann constant T over H. Okay, so again, you can plot this on a spreadsheet, but importantly, we've got energy and a thermodynamic property here. So it's a generic thermodynamic property. So we've gotten away from a gas dependence. That will conclude this video.